When I did this question, I actually took the wrong approach. I considered the different bags separately, basically, and called B1 the number of blue balls in the first bag, B2 the number in the second bag, and so on. And actually, that's not the way to do this. Um, we can write some things straight down. We know, I'm just now going to say B plus G plus R is equal to 20. Okay, in the real thing, like I would define what B and G and R are, that the number of blue balls, green balls, and red balls. And then we also have that there are half as many green balls as there are blue balls, which means there's twice as many blue balls. So B is equal to 2G. And actually, I can straight away substitute that in here. So I've got 3G plus R is equal to 20. And that is the main equation you need. Now, because I went with B1, B2, and so on, I kind of lost sight of this. This is the absolutely crucial equation. It's a Diophantine equation, and we can try to solve it for different values of G and R, see that it works. Like we could let G equal 6, for example. Look, you can immediately see that there's only going to be a certain number of solutions. But before we do that, there's another crucial thing, and that is the fact that we're told that there are at least 7 blue balls. So B has got to be, see, when I did it, I'd said that B1 was greater or equal to 7, but we can just say it in general, B is greater or equal to 7. And then overall, we've also got that R is greater or equal to 4. So these conditions will help us solve the Diophantine equation. There's not much else I can do. I can't simplify this, but I've got some conditions, I've got an equation, we can solve it, and let's have a go. So it's all about green and red, really. Um, Now, when I did this, I did look at G equaling 1, 2, and 3, but there's a little shortcut you can make. Because B is greater or equal to 7, then that means that 2G is greater or equal to 7. So G has to be greater or equal to 3.5. Actually, G has to be greater or equal to 3 because it's a whole number. So I don't have to, I don't have to look at 1, 2, and 3. I can go straight to 4. So reject G equals 1, 2, or 3. Okay, if you don't spot that, then you quickly get a value of B, which is not greater or equal to 7, and you can just reject it. So it's just a little shortcut, really. So if G is equal to 4, then we've got 12 here, and then R is going to have to equal 8, and then B is going to, we just have to add that to give 20, so B is also going to be 8, or we could double G. So in this case, we see that we've got the same number of red as blue, which is actually what we're trying to show here. I didn't even talk about that, but prove the total number of red balls in both bags is equal to either the total number of blue balls or green balls. Might just write down here, so R equals B here. Let's look at 5. So then I'm going to get 15, R is going to be equal 5, and B is going to be 10. Okay, so R is equal to G here. And if I take a look at 6, then I'm going to get 18, I'm going to get 2, and B will be 12. So this fails. R is less than 4 here, and will be for G greater or equal to 6. So I don't need to look at any more. Actually, that is enough. These are the only two possible situations, in fact, which is not what you kind of expect when you first look at this question. I mean, it's because we've removed the complexity of how they're distributed. We don't know if they're in the first bag or the second bag. It doesn't matter because we're only trying to prove a result about both bags. And actually, that's the key thing in this question. Don't start focusing in on details. It's more about the um, general kind of what is happening in both. So therefore, I just need to write a little conclusion. Therefore, these are the only solutions. The number of red balls is either the same as the number of balls or green balls. Gotta say, I struggled with this question somewhat, but it's a really nice one, quite unique, and who would have thought it? It actually just results in solving this Diophantine equation with these restrictions.